how the quantum world becomes classical. Decoherence, pointer states, and redundant reality.
All right, let's dive into one of the biggest, most mind-bending puzzles in all of science. I mean, look around you. Everything. The chair you're in, the screen you're looking at, it's solid. It's predictable. It exists right here, right now. But here's the crazy part. The fundamental quantum rules that actually build our world say it shouldn't be like that at all. So how in the world do we get our solid reality from all that quantum weirdness? Let's figure it out.
And to really frame this problem, let's go back to the master himself, Albert Einstein. As far back as 1954, he pointed out this huge disconnect. He said that this simple, everyday idea of an object having one definite location, what he called narrowness, isn't just something quantum mechanics has a hard time explaining. No, he argued it's flat out incompatible with its own core principles.
And that, right there, that is the mystery we're trying to solve. If every single thing is made of quantum stuff that can be in a million places at once, a million states at once, then why do we only ever see a baseball in a single spot? Why is Schrödinger's cat always, in our world, either alive or dead, and never ever both? To get to the bottom of this, we first got to really understand the two very different worlds we're trying to connect.
So let's lay it out. This is a classic tale of two worlds. You've got the bizarre, fuzzy realm of the quantum on one side, and our solid, everyday reality on the other.
Okay, so on one side, you have the quantum realm. This place is ruled by what's called superposition. It's where Schrödinger's cat can be literally both alive and dead at the same time. It's a world of pure, shimmering potential. But then there's our world, the classical realm, where things are definite. The cat is one thing or the other. A car is in a specific place. It's a world of concrete, solid reality. So the big question is, how does all that potential turn into something so concrete? Now, for decades, physicists had a couple of big ideas. The first, the Copenhagen interpretation, basically just drew a line in the sand and said, okay, quantum rules work over here and classical rules work over there. But it never really explained why the line was there. Then you got the many worlds idea, which is a wild one. It suggested that for every single quantum possibility, a whole new universe just splits off. It's a fascinating thought for sure, but it still didn't tell us why our branch, the universe we experience, feels so stubbornly classical.
Well, it turns out the Anson was hiding it in plain sight the whole time. It wasn't some mysterious new force. It wasn't some magical collapse of possibilities. The secret ingredient, the thing that forges our classical world out of that quantum fuzz, is the environment itself. Let's try an analogy, because this is where it gets really cool. Imagine a super delicate quantum state. That cat, being both alive and dead, is like a secret. Now picture the environment all around it, every single air molecule, every photon of light whizzing by, as a massive, unstoppable crowd of gossips, all desperately trying to find out what that secret is. This whole process actually has a name. It's called decoherence. And here's the thing, that quantum secret, it just can't be kept. The moment that system interacts with even one tiny photon or a single air molecule, information about its state leaks out into the open. The crowd of gossips finds out and the secret is blown. That fragile state of being two things at once is destroyed, and the system is forced to pick a side. It just can't be both anymore. But wait a second, decoherence is only half the story. I mean, it explains why these weird both things at once states die out so fast, but it doesn't explain why certain definite states, like a specific location or being either alive or dead, are the ones that consistently pop up as the winners. So out of all the possibilities, which ones get to become our reality? And this brings us to a truly beautiful and just powerful idea. It's known as quantum Darwinism. And yes, it's pretty much what it sounds like. Natural selection, but for quantum states. At the heart of this is a process called Einselection. Basically, you can think of the environment's constant monitoring as a kind of filter. Some quantum states are incredibly delicate. The slightest interaction and poof, they're gone. But, and this is the key, other states are uniquely robust. They're tough. These stable states are called pointer states, and they're the only ones that can survive that constant gossip from the environment. So let's just walk through this one more time. First, you have a system in a superposition, this big cloud of possibilities. Then, the environment is constantly monitoring it. That leads to decoherence, which wipes out all the fragile states. Now, inselection kicks in. Only the toughest, most robust pointer states survive that process. And finally, this is the Darwinian part. Information about those survivors gets copied over and over and over again into the environment. They become redundant. They're the fittest, because their information is the easiest to spread. To really get this, let's build a picture in our heads. Just imagine a system in superposition as this shimmering, blurry sphere, where every single point on its surface represents a different possible state. It's totally uncertain. Okay, you got that shimmering sphere? Now imagine the environment is like trillions upon trillions of tiny particles just constantly bombarding the sphere, bouncing off of it. And every single one of those collisions is like a little test, checking the stability of that particular point. So what's the result of all that? Well, under that relentless bombardment, the shimmering, blurry sphere, it just can't last. It's forced to freeze, and what's left are just a few stable, solid, definite points. Those points, those are the Einselected pointer states. That, right there, is our classical reality emerging from the quantum fog. Okay, so we have a process that selects for stable, classical-looking states. That's huge. But that only really explains why one object becomes definite. How does this whole thing create the shared, objective reality that you and I and everyone else can agree on? Well, the answer lies in one final, absolutely crucial ingredient.
And the secret is redundancy. See, the fittest information doesn't just survive, it thrives, it proliferates. The environment doesn't just make one copy of that pointer state's information, it makes countless, truly astronomical numbers of copies.
I mean, think about it for a second. You don't see a coffee cup by, touching it with your eyeball. You see the photons of light that have bounced off of it and then traveled into your eye. Those photons are just a tiny, tiny fragment of the environment. But because that environment is flooded with redundant copies of the cup's stable state, its position, its shape, its color, you, me, and everyone else can independently grab our own tiny samples of the environment, and guess what? We all get the same information. We all agree the cup is there. That agreement, that's objectivity.
And once you have this framework, all those classic nagging paradoxes just start to dissolve. The measurement problem is no longer some mysterious collapse. It's just information leaking out. Schrödinger's cat doesn't need a person to open the box. The environment is constantly looking, forcing a choice almost instantly. And you don't need infinite universes for objective reality. You just need the fittest information to be copied and broadcast everywhere for all of us to find.
This quote from Wojciech Zurek, who is one of the pioneers of this whole idea, just nails it. What we call reality and what we call information, they aren't just abstract ideas. They are physically tied to stable, redundantly encoded states that have literally won the evolutionary battle of quantum Darwinism. And so this leaves us with this incredible, kind of wild final thought. The world we see, the reality we all agree on, is the one that's been selected for its stability and its redundancy. It's the information that's easy to copy and share. But what about all those other possibilities? All that fragile, complex quantum information that got weeded out by decoherence? It might not make up our stable world, but it was there. And that really makes you wonder, what else is written into the quantum fabric of the universe that we're just not built to see?